Okay, you've labored long and hard over Geomath, and you're starting to feel like, well, maybe I should take on Mars Math. Good idea. Um, but in order to do that, you might want to be able to get there. So we're going to go off on a little bit of a tangent here and talk about the rocket equation. Uh, the rocket equation, is important because it basically tells you how much fuel you need to have, in a sense. You've got the initial mass, and the initial mass of your rocket has to have enough fuel to give you the velocity that's going to take you to your destination. In this case, let's say it would be Mars. So we have initial and final velocities, v sub I, v sub f. But we also have, we have a chemical reaction, or solid rocket fuel or liquid fuel. We're creating exhaust, which is pushing the rocket. So we have this speed to worry about, and we have the well, not to worry about. We have this speed to incorporate in the relationship, and we have the initial and the final masses, m sub I, m sub f. Notice that this is a logarithmic expression, so it will require you to use some of your skills that we've talked about and reviewed earlier on. And again, it's kind of a key equation to make sure that you have the fuel that you need in order to get you to your destination. So if we come back and we take a look at this logarithmic form and we ask ourselves, okay, well, how can I solve for m sub I, m sub f? Well, remember that these natural logs are powers of the base e. So how would you manipulate this expression in order to solve directly for the initial and the final masses? Take a minute. And if you did that, you would get this expression here. In other words, the log of m sub I over m sub f is the power that you have to raise the base e to in order to get this. So that just pops right out. When we take e to the natural log of m sub I over m sub f, we get m sub I over m sub f. This term we use as an exponent for the base e. And then we just solve for m sub I or m sub f, getting m sub I is equal to m sub f times the delta v, the final velocity, minus the initial velocity over the exhaust velocity. And for the final velocity, we get a minus sign in there, basically a delta v, minus delta v over v sub v. So one of the questions that you might have is, where does this relationship come from? And we know that as the rocket expends fuel, its momentum is going to change, and its velocity is going to increase. But the combined rocket and unspent fuel mass decreases. So its initial momentum will be m sub I times v sub I, assuming that the rocket has some initial velocity v sub I. It could be 0. And the initial mass includes the rocket mass and the mass of the fuel. So the initial momentum then would be m sub r plus delta m times the initial velocity. And its momentum at some time later would be m times the initial velocity plus the change in velocity. We've been burning fuel, we've been pushing the rocket, we've changed the velocity, we've also changed the mass, and that mass is associated with exhaust from the rocket, associated with the burning of the fuel. So our final momentum then is going to be equal to the initial mass times the initial velocity plus the change in velocity plus delta m times the velocity of the exhaust. And I do note down here, this is the Tsiolkovsky equation. You'll find a good discussion of this on the Wikipedia page for the rocket equation. And you can go to that for some additional information. I've tried to boil this down into parts. So we have, this exhaust velocity does come in two parts, and it depends on your reference frame. In the observer frame, that could be you standing on the Earth. It's going to be v sub e. But if you're inside the rocket, it's going to be little v sub e. Watching the action, you'll see the exhaust go off at a velocity v sub e. And then there's the rocket velocity v, or the initial rocket velocity v sub I. So the velocity of the exhaust in the observer frame has the component v relative to the observer, but it's also moving away from the rocket with velocity v sub e. So in the observer frame, v sub e is equal to v sub I minus little v sub e. Okay, so the sum of the forces is equal to the change of the momentum over time. And since there are no external forces, the mass carries along is being expelled from the rocket as exhaust, forcing the rocket along, and the sum of the forces are going to be equal to zero. And this just goes back to Newton's third law. And for every action, there is an equal and opposite reaction. So we're pushing the rocket in one direction, pushing the fuel in the other direction. Those two forces cancel each other out. One positive, one negative. However, there is a change in momentum, depending on what it is that you're looking at. We're looking at the momentum change in the final and the initial momentum of the rocket. So we have the mass times the initial velocity plus the change in velocity, and we have the initial velocity times the change in mass, and we're just going back to these two equations here, rewriting them over here, and just going through the algebra. So we should have had a subscript m sub I in there, but they're going to cancel out. So we'll cancel out these terms, and we cancel out these terms, and so we end up with an expression m times delta v minus the velocity of the exhaust times the change in mass. This is equal to 0. We have our delta p equal to basically these terms, at delta p. So the sum of the forces we already said is 0. That's the change in the momentum with respect to time. Force is equal to the derivative of the momentum with respect to time. And delta p is equal to m delta v minus v sub e delta m. So we have dp dt is equal to m times dv dt. We're just taking the derivative of each of these terms and looking at it in the limit that delta v and delta m go to 0. So we have m dv dt minus v sub e dm dt. And there are no external forces, so these are equal to 0. So m dv dt is equal to the velocity of the exhaust times the derivative of the the change in mass with time. Okay, so the rocket equation then, we've got m dv dt is equal to v dm dt. So this gives us that if we cancel out the dt's and divide this side of the equation by the mass, we end up with the differential velocity equal to the velocity of the exhaust times the differential mass over m, the mass of the rocket, and it is varying through time. So if we integrate this, we get the integral from the initial velocity to the final velocity of the velocity is equal to the velocity of the exhaust times the integral of the change in mass over the mass from the initial mass to the final mass. That gives us a change in velocity, delta v, this is just going to be v sub f minus v sub I. It's going to be delta v sub f minus v sub I here. Be the exhaust velocity, and we know that this integral is, if you remember back to some of our earlier discussions, the integral of dm over m would just be the natural log of m sub f minus the natural log of m sub I. But negative sign there corresponds to a division in terms of logs, so we end up with the delta v equal v sub e times the natural log of the ratio m sub f over m sub I, which we can rewrite in this expression. So this is your rocket equation. This is where it comes from, and we do change the sign here because our delta m is change in mass is mass which is heading in the opposite direction relative to the rocket. So we do change the order of the division here, and that's because of the direction that delta m is heading. And so let's try it out. Let's say we head off to Mars with an initial velocity of 0 kilometers per second. Let's say that we desire a final velocity of 12 kilometers per second. And the external velocity, exhaust velocity, is 5 kilometers per second. We've got our initial mass, m sub I, our final mass, m sub f, we want to solve for. What is that final mass? And so we're just plugging into this expression, which we just derived. We have a delta v of 12, assuming our initial velocity is 0. The exhaust velocity is 5. We've divided that delta v by 5. And then we have the log of the initial, solving for the initial mass that we need, the mass of the payload plus the mass of the fuel, divided by 9, which is the final mass, basically the mass of the payload. So take a moment and solve for m sub I. And assuming that you did that, we see that we get 12 over 5 natural log m sub I over 9. We take, this is just m sub I over 9. This is e to the 12 over 5, which is 2.4 over 5, or 2.4. And then we multiply that by 9, and we see that the initial mass of our rocket must be 99.2 tons. This ton is a metric ton, so it corresponds to 1,000 kilograms, and that gives us our desired velocity of 12 kilometers per second. So we may introduce some Mars math in the future, but this basically just is an introduction to the rocket equation, which is kind of a key part to being able to get to Mars, and it also illustrates a lot of the, several of the concepts and mathematical tools that we've worked with in the past. So see you next time. Thanks.